Alright everybody, here we go. We're going to start off official business this week by reviewing the things that we were looking at right before school got shut down. So we're going to we have been calling this section like Unit X. And what we're going to do here in this assignment, quote unquote, is do a quick review of what we're calling section X.1 through X.5. And then we're going to move on to factoring, which is X.6, X.7, X.8, and X.9. And then by the end of the week, you can take a little quiz or test, and that'll be it for the third quarter. But anyway, enough chit-chat. So these 12 problems should do a pretty good, thorough job of covering all the concepts from these topics. Anyway, so number one, all these were supposed to be simplifying, really, and so this says 3x to the second power times 2x to the fourth. But remember, it's technically 3 times x to the second times 2 times x to the fourth. Okay? And what we can do is we can do the 3 times 2. 3 times 2, just like back in, second grade or something? 3 times 2 is 6. And then in order to do x to the second power times x to the fourth power, when you're multiplying things together that have powers, and if the bases match, like both bases are x to the second power times x to the fourth power. So when you're multiplying like bases that have powers, remember the shortcut is to add the powers. So this becomes x to the sixth, because 2 plus 4 is 6. So that's where you add the powers. Number 2, when you're raising all of this to the third power, that whole bubble to the third power, you're going to raise everything in here, all the little factors in here, to the third power. And one of the things you got to remember here is when you are raising something to a power that already has a power, in other words, you're raising a power to a power, that's where you multiply the exponents. So for example, when you raise x to the negative 1 power to the third power, you're going to multiply the powers. But again, hey, don't forget about the 2, which is separate, and the y, which is separate. It's all getting raised to the third. And if you want to think of that 2 having a power of 1, it does technically, so go ahead. And technically you could say that's y to the first. So here we go. I'll play it like that. 2 to the first to the third, when you multiply the powers, the power of 1 times the power of 3 is 3. And then x to the negative 1 to the third, when you multiply those powers, you get negative 3. And then y to the first to the third, you multiply the powers and you get that. Now, as far as just cleaning this up or doing anything else we got to do, 2 to the third, since 2 is just a regular number, we could just say that's 8. 2 to the third is really just 8. But the bigger thing I want to emphasize here is negative powers. Like I should have included that over here in the directions. Simplify, and you should only have positive exponents in final answers. But then again, that really should go without saying. Don't expect that to be in the directions just because it doesn't say that in any directions. It's always there pretty much. Like that's something in general is always in play. So anyway, getting back on track. We have to fix that negative power. And we do that by dropping that part, the base with that negative power, we drop it down to the denominator, and we can make that negative power positive. So 2 to the third, which I guess we'll just call 8, and the y to the third, those are going to stay, quote unquote, stay in the numerator. But the x drops down to the denominator, and we're going to make that a positive power. So that would be a final answer worth leaving, okay, worth finishing with. Number 3. So now we're like dividing. This numerator divided by that denominator. So separate, right? The 9 divided by 3. Those are just regular numbers you've been working with since like 2nd grade. 9 divided by 3 is 3. Okay, those are the regular numbers. But then we have stuff with powers. X to the 4th power over x to the 1st power, technically. Okay? Now, hopefully you remember the shortcut here. We subtract the powers. This is where we subtract powers. So you end up with x to the 3rd, because 4 minus 1 is 3. And then 3 minus 2 is 1. And you don't really need to write an exponent of 1. So that's the answer there. Number 4, just kind of a few more examples of this type. 4 divided by 6. Well, my first reaction to that is not clean division. 4 divided by 6 is not clean, but it does reduce. Okay, don't make it a decimal. Don't do that. Okay, leave it as a fraction and reduce it if you can. So 4 over 6, that at least reduces to 2/3. And then as far as the bases with powers, again, we're going to subtract the powers. So it becomes x to the 0, 4 minus 4. And then, I guess, I don't think I meant it to be this way, but oh well. 3 minus 3, that's also 0. And so something I want to also remind you of is that when you have a power of 0, that always equals 1. Anything to the 0 power is just 1. Like this entire x to the 0 is going to get replaced with just 1. 5 to the 0 power is 1. 20 to the 0 power is 1. X to the 0 power is 1. And so same with the y to the 0. So actually the final answer is just 2/3. Number 5, 4 times, well, there's nothing really there to multiply the 4 with. I mean, technically there's a coefficient of 1 out in front, so whatever, but the bottom line is it's just going to be 4, and then x to the 2nd times x. What's x to the 2nd times x? Remember, there is technically a power of 1 there, and this is where you add the powers. Boom. Number 6, another example of, raising a bunch of stuff to a power. This already has a power. Again, technically the 3 already has a power, and when it's a power to a power, that's when you multiply the powers. So 3 to the 1st to the 2nd, it's just 3 to the 2nd. 1 times 2. And then as far as the x, 5 times 2 is 10. And if you want to say that 3 to the 2nd power is 9, go for it, because it is. All right, now changing gears a little bit. Get out of here, the cord. So now we're, again, changing gears. What can I say? What do we do with number 7? How do we simplify that or multiply? Right? 3x times that whole bubble of 3 terms. This is where you got to bust out the distributive property. So we do 3x times x squared, and I'm not going to repeat myself about how to do that. That ends up being 3x to the 3rd, and then 3x times negative 3x. That's going to be negative 9x to the 2nd. Remember, x times x is x to the 2nd, and then the 3 times the negative 3 is negative 9. And then 3x times positive 6 is positive 18x. And that's it. We're done because there's no terms that are alike that can be combined together. Number 8. Okay, now we're going to take the distributive property to the next level. Okay, because now we have a group of two terms here times a group of two terms. You know, these bubbles are directly next to each other, so they're being multiplied together. So one way to look at this is you don't just have to distribute the -1, you also have to distribute the 2x. So we're going to distribute the 2x and get, so 2x times x is 2x squared, because x times x is x squared. And then 2x times +4 is +8x. But we also have to distribute the -1. So -1 times x is -1x, or just -x. And then -1 times +4 is -4. And on this problem, you have to realize that there's some like terms that can be combined. So 2x squared comes on down, and then 8x minus 1x, or just minus x, is 7x. And that's that. This is also very commonly referred to, unless you're Birch, this is very commonly referred to as FOIL, okay? Because it's just a neat little acronym to help you remember all the distributing you're doing. When you multiply this times this, that's, you're multiplying the firsts together, and that's the F in FOIL. And then when you multiply these together, you're multiplying the outer ones. See how they're on the outside of, like the outsides? That's the O in FOIL. And then when we multiply this times this, that's like the inners, and that's the I in FOIL. And then when we multiply this times this, that's like the last term in each bubble. And so that's the L in FOIL. Anyway, so FOIL also applies here because it's like two terms here, two terms here. Firsts, outers, inners, lasts. So firsts, x times x, x squared, minus 5x, but then the inners plus 5x, and then the last, what's 5 times -5? That's -25. Now, once again, these are like terms. And it turns out here something special happens, And I'm referring to what textbooks call like special case examples. Because when these combine, they totally cancel out. That's technically 0x, but it's gone. And so your final answer is just that, And I want you to definitely realize how look at how these bubbles compare to each other. X plus 5 times x minus 5. Those bubbles definitely have a certain special relationship to each other. How similar but different they are to each other. How are they similar? How are they different, these two bubbles? And how these middle terms ended up completely canceling each other out. So your final answer looks like this. Just want to point that out. Few more to go. Number 10. This is just more distributing. If you want to think of this as taking the distributive property to an even higher level, because you're going to be distributing the x through this second bubble as well as distributing the 2. So we're going to basically multiply the x all the way through, and then we're going to distribute the +2. So x times 3x squared. That's 3x to the third. X times +x is +x to the second. X times -7 is -7x. Now we got to distribute the 2. 2 times 3x squared is positive 6x squared, because it's just the 2 times the 3 basically. And then positive 2 times positive x is positive 2x. And then positive 2 times negative 7 is negative 14. Okay, so now we have probably some like terms to combine, because that's when you're supposed to be simplifying, you can't leave terms that are alike that are not combined. So we have a positive x squared plus 6x squared. Remember, that's going to make it plus 7x squared. Then we have like a negative 7x plus 2x. Now remember, it's not just 7x, it's a negative 7x. The sign in front matters. It's included. Negative 7x plus 2x is actually minus 5x. And then the minus 14, no other terms like it. All right. Slightly changing gears, I guess, for number 11 and number 12. Here, I just want you to notice, okay, I mean, if nothing else, maybe, just please notice that this is not bubble times bubble. These bubbles are not being multiplied together. So don't do what you did in number 8. Number 8, okay, look at it, look at it. Number 8 is not the same type of deal as number 11. You're adding these two bubbles of terms together. I mean, if there's any distributing to do at all, it's like a positive 1 out in front of that bubble, and maybe even like a positive 1 out in front of that bubble. Like, that's the only distributing that you would technically do. But really, the bubbles just kind of drop. And all you got to do is like combine like terms. X plus x is 2x. And then negative 9 plus 6 is negative 3. And that's the answer. That's it. Number 12 is similar but different. How is number 12 a little bit different? Well, I mean, once again, we're not multiplying these bubbles together. There's just like a minus sign in between. And, you know, technically, I guess there's a positive 1 out there you could distribute, but here, what number is here? That's right, a negative 1. Now that is going to have like a serious impact once you distribute that. I mean, this is just going to stay 4x squared plus 2x minus 1, but distributing the negative sign or the negative 1 makes it negative x squared. You know, negative 1 times positive x squared is negative x squared. And then negative, so it ends up being negative 5x and then plus 4. Okay? Or positive 4, whatever. Same thing. And now we have, let's see, like terms. 4x squared minus x squared. Remember, technically there's like a 1, so 3x squared. And then positive 2x and a negative 5x, negative 3x. And then negative 1, remember, negative 1, it's negative. Negative 1 plus 4. Wow. Bunch of 3's. But that's it, people. Remember, have these written out on separate paper, or if you could print this very sheet out, all the better. Snap a pic, make a scan if you're that well equipped. I don't know, but turn that sucker in.